Hello and welcome to my talk. My name is Bruno Morabito and I'm working at the Otto von Guericke University Magdeburg in Germany. And I would like to present our paper on multi-stage event-triggered MPC for automated trajectory drilling. In automated trajectory drilling, the goal is to control a drilling bit to follow a predefined path, also called well plan, which will basically connect the rig at the surface with the oil deposit. The drilling bit, in this case, we are using a bit which can be controlled by actuating so-called ribs. So they are basically pistons that can push against the rock formation, and by bending the bit we can steer the bit in different directions and make this follow a well plan. The bit at the is almost always controlled from the surface, and the control signals are sent to the bit, and measurements are sent from the bit to the surface by using a mud flow variations or pressure wave, which travel through a mud which is constantly pumped into the drilling string. This system is called Pulse Telemetry, and it works like this one. So the controller is on the surface, a control action is sent through this Pulse Telemetry through the so-called downlink, and then the measurements from the drilling bit are sent uplink to the same Pulse Telemetry system. The advantage of using the system is that it's wireless, so it does not require expensive cable that has to go through the string. But disadvantage is that it has a very low bandwidth, so you have a limited amount of data you can send to the surface or downhole. It's slow, and as the operations, so drilling operation must be stopped, must be paused when we send a downlink, and this downlink can last from 5 to 10 minutes, so it definitely slows down the process. So the first objective we had in mind was to reduce the cost of operation by minimizing the downlink number, because it's linearly correlated then to the amount of time we need for drilling. The other challenge that we had in mind was that we are drilling in a highly uncertain environment. There are many sources of uncertainty, such as you can imagine the rock formation, and also the string dynamic plays an important role. We have hundreds of meters of string, and the dynamic and now the string will react to the control actions will depend on its geometry and also on the geometry of the bit. The uncertainty comes also from measurements. In particular, azimuth measurements are particularly noisy, and also the uncertainty can affect the control actions. While what we want to do, we want to satisfy some constraints such as dogleg severity, or for example, we want to avoid hard formations because by basically drilling around them. So the second objective we had in mind was to have a method which help us to robustly satisfy the constraints. So keeping these two objectives in mind, increase robustness and decrease the number of control actions, as we said, we can pick now two tools coming from different control areas. One is robust control and the other one is low attention control. From the robust control part, we decided to use the multi-stage MPC approach, and for the low attention control, we used the event-triggered MPC. So we basically merged them together into forming a multi-stage event-triggered MPC. And now in the next slides, I'm going to give you a short recap on multi-stage and event-triggered MPC. In the multi-stage MPC, basically a scenario tree is built, instead of the MPC, instead of having a single prediction as a scenario tree of predictions, the branching of the scenario tree is due to a parametric uncertainty. So it's assumed that the parameter can take finite values or finite so-called realizations, and at every point of the prediction horizon, it's assumed that all the possible realization occur. So at every point of the prediction horizon, you will have as many state prediction as many branches you have. And this, as you can imagine, will grow with the prediction horizon exponentially. So, and this will soon end up being a very computationally demanding problem to solve. So what is usually done, we use a robust horizon and we stop branching the scenario tree at a certain prediction length in order to keep the computational time low. And this makes sense if you think that the prediction, the uncertainty far in the future from the current point does not generally play a fundamental role at the current time. So if we assume that the parameters of the system do take the values which are considered by the scenario tree, then we can guarantee also robust constraint satisfaction. In general, that's not the case. So the parameters considered by the scenario tree are not exactly the parameters of the system, but nevertheless, the degree of robustness, let's say, in terms of how much we violate the constraints, that increased. Now, if instead we want to add to this approach the event trigger MPC, then the idea works as follows. What we did, we created a virtual corridor along the well plan. We decided what is the maximum length that we allow the predictions of the MPC to be from the well plan. Now, if any of the predictions of the scenario tree, in this case represented, for example, 3 predictions, if any of those violate the corridor around the well plan, then a new MPC iteration is triggered. As long as this does not happen, the old control action is kept into the system. Those are the conditions. It's a bit looks complicated, but just says that we triggered a new MPC iteration whenever any of the predictions violate the constraints, so violate the corridor. So this is a summary of the control loop. We have at the surface an MPC which has the model of the system and the constraints. The MPC, when it's triggered, sends a control action through a downlink using the Pulse Telemetry to the drilling bit. In the drilling bit, we have our sensors that measure the quantity we need, and they are sent back to the surface through an uplink. The event triggered condition decides whether it needs to trigger a new MPC iteration or not. Now, we can also prove recursive feasibility of the MPC. In this case, I'm going to give you a short idea of how this could be proved. For details, you can refer to the paper. The recursive feasibility is based on a simple idea. We say instead of having one model which have different parameters realizations, we have a set of model with different parameters that you see on the right side. So if we assume to have a common control invariant region for all these models, then we plus some other assumptions on continuity and compactness of the sets, we can guarantee recursive feasibility of the multistage MPC. And this is this has already been proved 5 years ago. But now we want to add the conditions for recursive feasibility for a multistage MPC with event triggering. The first thing we do is to linearize the system. Then we assume to have a set sigma 1 being a control invariant set, then if we assume that even when no control input is used, the system remains within the control invariant set, then we can also prove recursive feasibility of the event-triggered MPC. Just to give you a general idea how this works, then you can refer to the paper for more details. Now coming to the first results, so we need to satisfy some constraints. In the case we considered, we have basically two main constraints. One is the dog-leg severity, and the other are input constraints. That's less important. Dog-leg severity is something which is very important during drilling. It basically expresses the degree of bending of the bit. We want to avoid high dog-leg severity because this would cause, for example, mechanical ruptures of the bit. So this is one of the constraints we want to satisfy. The objective function looks as follows. We want to weight the distance to the well plan with the first term. Then we have the dog-leg severity, which also appears in the objective function, so it does not only appear in the constraints, but also in the objective function because you want to minimize that. We also weight in the difference, so the change in input. And then we have a terminal cost where also we have the distance of the plan. Now we are going to compare this approach without event-triggered MPC without multi-stage. So nominal event-triggered MPC to see whether robustness was improved. Here I'm showing the results for the event-triggered MPC alone. I'm plotting the dog-leg severity. The red line represents the dog-leg severity limit we don't want to exceed. The blue line represents the predicted dog-leg severity, while the black line is the real dog-leg severity. In this case, we simulated two changes in model parameters. The first change occurs at a depth of 250 and the second change around 350 meters. And these are represented by the vertical lines. In the first section, before the first change, the parameter, the system, and the parameter, the model match, so there is no constraint violation. After the first change, there is a parameter mismatch, and we see that the dog-leg severity limits are not anymore respected. And there's a difference, of course, between the real dog-leg severity and the predicted dog-leg severity. After the second change, there's an even greater parameter mismatch, so the uncertainty limits are also exceeded more than before. Now, if we consider the multi-stage event-triggered MPC, we see that in the first two sections there's no constraint violation, and this is due to the fact that now there are, first of all, more predicted dog-leg severities. You see there's more blue line, and this prediction comes from different scenarios of the scenario tree. And in the first two sections, there's at least one scenario that considers that parametric uncertainty because the parameters we choose were within the uncertainty considered by the scenario tree. In the last section, we used a parametric uncertainty that was outside the uncertainty considered by the scenario tree. So we do have a light constraint violation, but it's much smaller than the one of a purely event-triggered MPC without scenario-based. And we did this one we did this case to study what happened if the parametric uncertainty is outside the uncertainty considered by the scenario tree. Even though the parametric uncertainty outside the one considered by the scenario tree, you still have an increased robustness. When it comes to the distance to the plan, both methods work the same way. So we have a distance to the plan, as you see on the left graph, that is below 1.5 meters, which is good. And then the difference is in the triggering interval that you need to have to achieve this distance to the plan. We are comparing the nominal MPC, so vanilla MPC without any triggering event, the event-triggered MPC and the multi-stage event-triggered MPC, and we are showing here the triggering interval in meters. So how often in meters you have to trigger a new MPC iteration. While the normal MPC, but by our definition, triggers the new iteration every meter. The event-triggered MPC, using the corridor idea I discussed before, triggers an event every 21.7 meters, while the multi-stage event-triggered MPC triggers an event every 23 meters. So the frequency decreased, which is also a good result. And this is because the uncertainty is now considered in the prediction of the MPC, so it's much less likely for the MPC to violate the corridor and therefore to trigger the new MPC iteration. So we have an increase in triggering interval. So the second objective was also achieved. Now to conclude, we said that the automated trajectory drilling tries to follow a predefined path in the most efficient way as possible. We said that the drilling takes place in a highly uncertain environment, and that we need to satisfy constraints despite the uncertainty, and we need to decrease the control actions. Those were the two goals. We propose a multi-stage event-triggered MPC that tried to increase the robustness, decrease the control action, and we show that this is possible. We know that this the uncertainty it can be reduced by increasing the model accuracy, but building first principle model of a drilling string is very complicated. So what we are currently doing is we are trying to use data-driven models that would augment and would increase the accuracy of the first principle model, and then use that in a closed loop with MPC. So this concludes my talk. Thank you for your attention. If you have any question, I'm happy to answer them.